This video illustrates a possible FPGA and software development cycle in Linux for the Microsemi SmartFusion device. This demo runs on the MCraft A2F LNX EVB board included in the Linux SmartFusion evaluation kit. The main concept is that Linux running on SmartFusion, NFS mounts a directory on a development host, making host files and directories immediately visible to the target. This way, I am able to develop my code on the host and immediately test it on the target, without the need to reflash or even reboot Linux on SmartFusion. The Linux SmartFusion distribution provides a sample project called Developer that is intended as a template project that can be used to jumpstart development of custom user space applications and loadable kernel modules. From the kernel configuration startup sequence perspective, Developer is all ready for NFS mount. From the BusyBox configuration perspective, Developer enables the insmod, lsmod, rmod commands in a multi-call BusyBox binary to allow management of loadable kernel modules. Structurally, the developer project has a subdirectory called app. This app directory contains loadable device driver implemented as a sample.c file, which implements a device driver for a pseudo device that returns a certain string on attempt to read the entire device and rejects any attempts to write to this device. It also includes a user space application implemented in app.c, which opens the sample device driver using a /dev/sample device node, reads the device until an EOF on a per byte basis is recorded, and prints the read characters to the user terminal. These source files are intended as a starting point for development of new user space application and device driver. The development of new code is to create a clone of the developer project. In the Linux SmartFusion development environment, there is a make goal that allows us to do exactly that. Here is how a new clone of developer project is created. I'm going to call the new project Test1. Now I go to the new projects directory and update the target startup script so that it automatically mounts the new project's app subdirectory from the Linux SmartFusion installation on the development host. This makes the app subdirectory immediately available on the target, allowing me to edit and build my applications and loadable device drivers on the host, and then test them on the target. Now let's build the new project. This being a first build in the new project, the build is going to take a bit of time, so I will fast forward to the end of the make command in this video. Now that I have a bootable Linux image for the new project, I will copy it to the TFTP server directory on the host so that I can load it to the SmartFusion from U-boot over TFTP. On the target, I hit reset in order to get to U-boot. Interrupt the U-boot auto boot sequence by pressing the spacebar, and from the command monitor, I update the U-boot environment so that it boots Test1 project over TFTP. Here we're booting the new project over TFTP. From the Linux shell prompt, I'm going to check that the NFS mount is successful. Then go to the NFS mounted directory and test that the current version of the application and device driver work as expected. At this point, we are all set to start development of new code. Unless we do something wrong and manage to crash the kernel while developing a new device driver, we should be able to develop new features without having to even reboot Linux on the SmartFusion. The functionality we want to develop in this demo is 1. Add to the existing FPGA logic a GPIO that software will be able to use in order to light or unlight the user 1 LED connected to an FPGA pin of the SmartFusion on the A2F LNX EVB board. 2. Modify the device driver such that each write access to the driver, regardless of the size and content of the data being written, toggles the state of the LED. And 3. Modify the user space application so that it calls write on the device node in a loop, making the LED blink at a certain rate. The first step is to update the Libero project for the A2F LNX EVB board and to add an appropriate GPIO IP block to the FPGA logic. In this demo, I'm not going to show how to use the Libero IDE or how to modify a project's FPGA logic. That can be saved for another demo. Let's just assume that I have updated the Libero project for the A2F LNX EVB board in such a way that 1. There is a soft IP GPIO that controls the user 1 LED on the A2F LNX EVB. 2. The default state of the GPIO is such that the LED is lit. And 3. Software can change the state of the GPIO. The register that controls the LED is mapped at a certain address at the Cortex M3 memory space. Writing a 0 into the register unlights the LED. Writing a 1 lights the LED. I have copied the updated Libero project in the DAT format to the app directory on the development host, which, as discussed above, makes the files immediately visible to the SmartFusion device. Instead of burning the new FPGA design over JTAG, I'm going to use the IAP tool on Linux, which is specifically designed for runtime FPGA fabric upgrades of the SmartFusion. With IAP tool, FPGA self-upgrades are performed natively on a running Linux system and do not require additional hardware, such as the Flash Pro 3 or 4 programming device. Here is how the IAP tool is run. One interesting thing about IAP tool is that as soon as an upgrade command completes, the new image has been installed into the FPGA fabric and is running. No reset or Linux reboot is required. Here you can see that the user 1 LED lights up immediately on completion of the IAP tool invocation, which is an indication that the updated logic is running. It is important to note that the FPGA fabric is held and reset during execution of IAP operations by IAP tool and cannot be accessed by Linux software drivers. Due to this, it makes sense to run device drivers for FPGA-based controllers as kernel modules, and to unload all such modules before running a fabric upgrade using the IAP utility. As I will show in this demo a bit later, I am going to run my device driver for the LED as a kernel module, which makes it possible to upgrade the FPGA fabric with the updated designs as many times as needed. The next step is to modify the sample device driver so that it provides the required interface for toggling the LED state. To recap, here's what we want to get. First, each write access to the device, regardless of the size and content of the data being written, toggles the state of the LED-controlled GPIO. Next, a read returns an EIO error which corresponds to an unsupported I/O operation. So, I just go to the development host, invoke the editor on the device driver C file, and do the obvious modifications to the code. I'm not going to show the actual editing in this video, but here's what the resulting code is going to look like. As you see, the code is very simple. The write entry point just writes a 0 or 1 to the LED controlled register, toggling the state of the LED. Now I'm going to build the updated driver on the host. It builds just fine, so now I'm going to try it on the target. First, I install the driver as a kernel module. Now I am ready to actually try it. Since all I need to do is change the state of the LED is to call an arbitrary write on the device, I will just run a standard echo command redirecting its output to /dev/sample in order to toggle the LED. As you can see, this works as expected, and I can change the state of the LED by simply making a write call to the driver. The next step is to make updates to the user space application so that it calls a write in a loop in a way that makes the LED blink at a certain rate. Again, I'm not going to show the actual file editing in this video, but here's what the resulting code will look like. Again, the code is very simple. It just opens the device node and goes into an endless loop, calling a write and then sleeping for a second. Now I'm going to build the updated application. The code is very simple, so it builds just fine. Now I'm going to try it on the target. The LED is blinking at a 1-second rate, so all works as expected. Actually, this sample interface being so simple, we didn't even have to write a user space application to get the LED blinking at a specific rate. We could do the same behavior using the following simple shell script. This, by the way, illustrates how shell scripting can be used in Linux to help in application development. As a final step in this development session, let's unload the kernel module from the kernel. When our mmod completes, we are ready for our next iteration of device driver development, should we need to make it more complex than it is now.